All right, line A6, learning task 7. Today we're going to take a look at thyristor applications, and I am not going to lie, this is going to be probably the heaviest application of electronics that you are going to go and have across all 4 years of your apprenticeship. This is really where we're starting to go and take all those individual little blocks and put them together like, a pile of Lego to create something much more big and much more awesome. We're going to go through a couple of circuits. We're going to go and use the fundamental principles of thyristors, the fact that we need to have holding current on them. We're going to use the fundamental principles of grounding or switching to ground, whether we've got something syncing or sourcing, as well as AC and rectified AC, that we're always going to be dropping back down to that zero, which is going to go to shut off a lot of our components. And you're going to see for a lot of our components that we're going to go and have just bridge rectification. The reason we like bridge rectification on the first one over here, on the second one over here, not on that one, but on the third one over here, is because on all three of these, every single time that we go and hit that value of zero, or we commutate the voltage, then we are going to go and lose holding current. There will be zero holding current at this point because we're going to go back through that value of 0 volts. So it's going to make it really handy for us to be able to go and know that every time we alternate, we're going to shut stuff off. All right, the first one that we're going to look at is going to be a DC speed control for motors. First of all, DC motors have got two ways that we can go and control them. We are going to cover DC motors later on. We're going to have a rated speed. Let's say that our rated speed is 1800 RPM. That 1800 RPM, we're able to go down from that 1800 RPM all the way down to 0 RPM, or where we would say that the motor would be shut off, by controlling one component of the motor that is going to be called the armature. I'll just write arm in there right now. If we want to go greater than the 1800 RPM, we can actually go above base speed if we've got a shunt type of motor and if we go and control the shunt field. And if we change the shunt field resistance, we're going to be able to go, not unlimited, but we will be able to get to higher than our base speed with them. So we really have got a couple of ways that we can bring ourselves, either low or high based upon what we have for this 1800 RPM or our base speed. As the load changes, you're then able to go and adjust either one of these, the armature or the shunt field, and that's going to allow you to go and change what's happening in the circuit. Make sure, you can maintain this constant speed or something like that. Okay, let's take a look at this one though over here. This one, what we are going to be controlling is we're going to be controlling a motor part over here called the armature. Since we're controlling the armature, therefore we must be looking at controlling this thing between 0 all the way up to its rated speed. We've got another motor component inside of here, which is this F1 and F2. F1 and F2 is just going to be the shunt field. It's going to be a field, and by a field we just mean a coil of wire that is going to be placed inside of there that's going to be powered up and it's going to create a magnetic field. And since this has created a magnetic field, we'll stick some magnetic lines of force around there, they're going to go and interact with the armature, and then that's what's ultimately going to go and give us rotation. That theory will be covered later on. For now, you just need to know that it exists. First of all, we do need to go and have constant power to this field. If we don't have constant power to this field, we're not going to be able to establish that initial rotation. And if we lose this field later on, we would go into overspeed, we'd go above speed. So we're just going to leave this thing because we're not trying to vary above speed. We're going to leave it directly connected across here. This thing here, the DB, is just going to be a diode bridge. That's all that it is we have got a bridge type of setup. You can hear these things referred to as, some people call them Wheatstone bridges. That's incorrect. Wheatstone bridge is for resistance, but you're going to hear bridge or H type of control that you're going to have. And it's just going to be a full wave bridge rectifier, which means that my AC that comes into here, looking like that, is going to go and have all the bottom sections chopped off and flipped up. So we're going to go and get pulsating, full wave rectified AC. It's going to look like that. The black line that we have up top, let's erase the red one down there. So that's what that bridge is going to go and do. Once again, that important part is that we are going to be hitting that point where we have 0 volts, and therefore we are going to hit that point where we are going to have 0 amps of holding current. Okay, let's go through this thing. We're going to just take a look at this thing starting from a value of 0 volts, and we're going to go and watch that voltage rising. First thing that I'm going to go and look at is this, which we have seen before a couple of times. It's an RC timing network, and we've gone through this on previous ones where we say, look, all that happens is that if we've got DC and AC, we know where a positive is, we know where a negative is. They show them on the bridge over here. We're going to go and have electrons that are going to be traveling through here, that are going to build up on this side, driving electrons away over here, and those electrons, the only way for them to get out is to travel through here. They can't go through this diode because this diode, during a positive alternation, is going to go and be reverse biased. So we are going to go and have electrons that are going to go and travel through there. As these electrons travel through here, repelling them from the opposite side, we are going to go and see the voltage that is going to be seen across here. This voltage is going to go and be rising. And eventually we hit the point where that voltage is going to be great enough to go and overcome whatever our diac voltage is. Remember, that's set by the manufacturer. So the manufacturer is going to select, maybe we've got this thing set to, 10 volts or something like that. Plus, we have to overcome what we have over here for our gate voltage. We'll call this 0.7 volts over here, which means that overall, what we're looking for is we're looking for approximately 10.7 volts. So we just need to go and build up electrons till we hit that magical number of 10.7. And once we hit 10.7, this diode that was previously blocking is all of a sudden going to go into conduction. And when it goes into conduction, what does it do? A couple of things. First of all, it is going to go and allow all the electrons that have built up on here to go and travel through this pathway back over here. It's going to neutralize the charge on that capacitor. That bump, when this thing turns on over here, we're going to get all those electrons that are going to rush through here. As those electrons rush through here, we're also, because this thing has now gated, it's acted as if it's a closed switch, we've got a positive voltage that's applied over here, which means that this SCR is going to go and turn on. And when that SCR turns on, something wonderful and magical happens. That is that we are going to go and get current flow, which is now going to be able to travel through that armature over there. So what we'll be able to do is we are basically using this RC timing network to go and choose how far into the cycle do we turn it on. If I've got a low value of resistance over here, this is going to charge up quickly, which means I'm going to get almost a full wave that's going to go in. If I go and increase my amount of resistance, this thing is going to go and turn on much later on. So I'd get less average value of voltage that I would go and get over top of this motor. This, by the way, what we're looking at over here is the motor one. And if I were to go and increase it far enough, my resistance, I could get past the point where I've hardly got any voltage at all, and I'd actually be able to bring this thing down to 0 volts. Each of these over here just shows my resistance increasing. As I would increase my resistance, I'm going to get less and less effective area that I'm going to be able to carry through these. It's a wonderful thing. The great thing as well is that this SCR, every single time that we go and hit this 0 over here, is going to go and shut off. So we don't have to worry about it staying on, holding current through to the next cycle. It shuts off right over here, and then we wait, boom, the next cycle turns on based on that value of RC that we have over here. A couple other components that we want to take a look at inside of here are going to go and be these diodes, diode 1 and diode 2. All right. Diode 1 and diode 2 are in here simply to go and control stuff. If this voltage over here, if we're looking at it, I'll just erase all of this actually. If we're looking at that waveform is going to go up, and that waveform is going to go back down. We've got an AC supply. This is probably going to be a peak of 170 volts if we're coming off of a 120. And what we're going to have over here is going to be a value of 0 volts. How high does this cap charge up? Well, really dependent upon the amount of resistance inside of here. If we have a super low value of resistance, we could theoretically charge it all the way up to 170 volts, which would not necessarily be good, because then this thing would stay on, the diode would stay on, and the SCR would go and stay on. So because our cap follows the voltage, right? Whatever we have on here, the cap is going to go and follow that. We're going to just say that we can charge our cap up to this level over here. We're going to call this thing 100 volts. Let's say that we've set the resistance so that we can get enough electrons through. This thing can charge all the way up to 100 volts. This thing is always going to go and nuke that, allow that to conduct all the way through here, which is going to drop that value of voltage as well. And as it drops that value of voltage, it's going to bring it down to a much lower value of voltage. But that value of voltage that's going to drop to is never going to be actually truly 0. What happens is there's going to be a point where this thing's got a small amount of voltage left over top of it, and it will be biased positive, negative. So I'm going to do that right now. Positive here, negative over here. We're going to call this thing 5 volts, okay? Let's say that it stays at 5 volts because we know that we need to get this 10.7. So actually, we're going to keep this thing at 10 volts. Because if it was greater than 10 volts, this thing would have conducted and it would have discharged itself. So it knocks itself down to this 10 volts. What happens is that my main applied voltage drops away to 0 volts. And when my main voltage drops away to 0 volts, now I've got 0 volts over here, right? 0 volt supply. This is now going to be the greatest magnitude of voltage that's left inside of this circuit. And if I trace through its path, I see that I've got a positive from this 10 volts that is attached to this diode 1, which all of a sudden now is going to be conducting because I've got a positive to that anode. And then I've got a cathode, and then I've got my electrons, which can go somewhere. Where are they going to go? They're not going to go through the supply. They're not going to travel through here because this is going to go and send them back to themselves. They're not interested in that. They could possibly go through here, except for the fact that this SCR has shut off, which means that there's really only one path left, and that is they go through this field that we are going to go and have. What you'll note about it as well is because it is negative over here, here's where the electrons are, here's where the holes are, those electrons are going to be traveling through the field in the same direction as my main current would have been traveling through the field. It helps us to maintain magnetization on there, and it just allows, this diode over here, allows us to go and knock off all of that voltage, which basically resets our cap that we're going to go and have over here. It's a beautiful, wonderful little thing. If we don't have that in there, what we would get is we would have phase control for just the very first one, and then after that we would just have full wave control because we'd always be keeping this thing charged up to basically that dioc value of voltage. So we need to have that one in there. The other one that we have over here is going to go and be this one, diode 2. And diode 2 is in here because we have got a motor armature. Armature is going to be the rotating part, which means that if there's rotation, remember we've got current that is always discharging through here. We have got rotation, we have got flux, we have got everything that we need to go and generate voltage. EG is equal to BLV. Flux density, we're getting that off of the current that is being discharged from this cap through here. So that's our flux density. Length of wire, absolutely there's length of wire that's going to be inside of here. It's made up of windings. And velocity, there's going to be some momentum. So this thing is always going to be, rotating, which means we can generate values of voltage. It is also made up of coils of wire, and coils of wire have this thing called inductance. And inductance is an effect where we try to oppose any change in current. So if my current was traveling through before in this direction, see how it's negative to positive? If my current was traveling through before, all of those magnetic lines of flux that we have around there, when we shut this off, are going to go and collapse back inward and try to maintain that direction of current. Before, when this SCR was turned on, I'm just going to draw this line out over here. When this SCR is turned on, this armature would then be acting as a load because it's being driven by this over here. But when we go and shut off this SCR that we have down here, so a big red X through it, when that shuts off and when this thing is just coasting and collapsing fields back in, it now turns into a source. How does voltage travel through a source? Well, voltage travels through a source from positive to negative. And if this is the direction of current that it's trying to maintain, and if it's now a source, therefore this end must be positive, this end must be negative, and oh my goodness, would you look at that? All of a sudden, when the SCR is turned off and this is coasting through, we have got proper polarization on diode 2. We see that the anode is connected then to the positive, the cathode is connected to the negative, which means that we are going to be able to go and take any of that induced current and just run it off through here. This is what we have referred to inside of second year as being a freewheeling diode. We were looking at them as single phase inductors. Now we're using it on a rotating inductor, which is going to be our armature of our DC motor. That's pretty cool. Okay, so that is our speed control for the DC motor over here. We will move on next into our regulated battery charger.